All right, today we are diving deep into the tiny, brilliant universe that lives right inside your phone screen. We're going to unravel a story about wasted energy, some pretty strict quantum rules, and a super clever molecular heist that's making our displays brighter and way more efficient. Let's get into it.
So let's start with a really surprising question. Did you know that every single time you fire up your OLED TV or your phone, up to 3/4 of the electricity is just gone? It doesn't become light. It's basically wasted. So where on earth does it go?
Well, the answer comes down to these little energy packets called excitons. You see, when electricity flows into your screen, it creates them. But here's the kicker. Only 25% of them, the ones we call singlets, can actually produce light right away. The other 75% are called triplets, and they are, for all intents and purposes, dark states. They're packed with energy, but they can't release it as light. They're just stuck.
And this, right here, is what scientists call the 75% problem. It's been the central puzzle in making our displays and lights perfectly efficient. I mean, how do you go about rescuing that massive chunk of energy that's just sitting there, completely wasted?
So let's properly meet our two main players in this story. On one side, we've got the useful singlets. They're the heroes or the ones giving us light. And on the other side, we have the wasted triplets holding all this incredible potential but totally unable to use it. The whole game is figuring out how to get those triplets to act more like the singlets.
And that's where the hero of our story comes in. The whole goal is this kind of quantum rescue mission, converting those useless, dark triplets back into light-producing singlets. This amazing process has a name: thermally activated delayed fluorescence, or just TADF for short. And believe me, it's the key to unlocking all of that wasted 75%.
Okay, so to really get how TADF pulls this off, we need to zoom way in. I'm talking about what happens inside a single molecule in just a few tiny fractions of a second. It's a super fast timeline of events.
So if you look at this timeline, step 1 is when our singlet and triplet states are born. Then, in step 2, the singlets do their job and immediately give off light. But the real magic, the absolute key to this whole thing, happens down at step 4, reverse intersystem crossing, or RIS. This is the heist itself. This is the moment where that dark triplet finds a way to flip its spin, become a light singlet, and give us a whole second wave of light. Now here's what's so fascinating. The most direct, most obvious way for that triplet to turn into a singlet is, well, it's basically forbidden by the laws of quantum mechanics. The front door is locked. The molecule can't just flip its spin whenever it wants. It has to pull off a really clever trick, a quantum heist. And this gets to the very heart of the problem. That direct spin flip relies on something called spin-orbit coupling. You can think of it like the molecule's internal compass for flipping its spin. But in these molecules, that compass is just incredibly weak. It's slow. So waiting around for that to happen just isn't going to work. The molecule needs a backdoor. It needs another way in.
So how does this two-step heist actually work? It's brilliant. First, the disguise. The triplet starts to vibrate in a very specific way, and this wiggle allows it to mix with and sort of borrow the identity of a different triplet state nearby. Then, step 2, the switch. Now that it's wearing this disguise, the quantum rules that were blocking it are relaxed, and bam, it can easily flip its spin and become one of the good guys, a light-producing singlet. So this idea of a disguise and a switch is cool, but how does it really work at the quantum level? Let's break down the actual physics behind this incredible molecular trick.
Okay, so that disguise, it's made possible by something called vibronic coupling. This is a wild quantum idea where the literal physical movement of the molecule, its vibrations, its wiggles, gets directly linked to its electronic personality. It's kind of like a dancer changing their entire shape to interact with a partner in a new way. By vibrating in exactly the right way, the triplet changes its electronic shape, and that's what gets it ready for the big spin flip.
So the whole point comes down to this contrast. The direct path is like trying to run through a brick wall. It's weak, it's slow, it's pretty much forbidden. But this spin vibronic path, that's like finding a wide-open side door. It's a much stronger, faster, and totally allowed pathway for that energy to travel. It's the secret to making TADF work so well.
And this slide, this is the secret formula. It's not one single event, it's a 1-2 punch. It's what's known as a second-order process. You have the vibronic mixing, that's the disguise, and you multiply that by the spin-orbit coupling, that's the switch. And when they work together, they create this super powerful and efficient pathway that just didn't exist when they were separate.
So now that we've cracked the code on how this whole quantum heist works, what do scientists do with that knowledge? Well, this is where theory becomes technology. This is where we start engineering molecules to be the perfect little heist artists.
And it turns out there are two main design rules for making the perfect TADF molecule. First, the energy gap between the triplet and the singlet state has to be tiny. That makes it really easy for the triplet to get just a little bit of heat from its surroundings to make that uphill jump. And second, and this is so crucial for our heist, you need a mediator state at almost the exact same energy level. This ensures the vibronic disguise is as convincing as possible.
And, scientists don't just guess and check. They use incredibly powerful computers to simulate this entire process before they even make the molecule. They model its shape, they calculate all the different energy states, and they compute the strength of both the vibronic and the spin-orbit couplings. And from all that, they can predict with amazing accuracy just how fast that triplet to singlet conversion is going to be.
So what's the result of all this hard work? What's the big payoff? By understanding and engineering this incredible spin vibronic mechanism, we can now design OLED molecules that have nearly 100% internal quantum efficiency. Think about that. It means that basically every single electron you put into the system comes out as a photon of light. That wasted 75%, it's gone.
So, what are the big things to remember from our quantum heist? First, that rescue of the dark triplets, it's usually a two-step second-order process. Second, it's not enough to just make the energy gaps small. You have to be a molecular architect and carefully engineer the electronic character of all the states involved. And finally, by perfectly matching up those molecular wiggles with the right energy levels, you can effectively just turn on this super-fast conversion pathway, unlocking near-perfect efficiency.
So we've gone from a world that wastes 75% of its energy to one where we can control light with almost perfect precision. And that just leaves us with a final really exciting thought. What does a future of ultra-efficient displays, lighting, and maybe even new kinds of sensors actually look like? The possibilities are, well, they're literally brilliant.